This video is about definitions and classifications of differential equations. So we're gonna cover elements that we need in order to differentiate between different types of differential equations and some naming conventions that are useful in order to talk about differential equations. So let's go into it. A very broad definition of differential equations is that you're taking a function, u, the variable that function depends on, and here I call it x, all possible derivatives of the function u, so the first, the second, and so on, and you merge all of this into a huge function, capital F, and you want that capital F to be equal to 0. This is a very abstract way of looking at differential equations. So what does it mean? It means that we're defining a function u by what we know about how it behaves with relation to its derivatives. So we have some understanding about how the derivatives of u behave, and that is what we use to look for u. We're interested in finding a solution to an equation, and the solution we're looking for is itself a function. So let's look at some more specific type of differential equations. The very first type is we're looking at u that is a function of just one variable. So we're writing either u of x, sometimes we're going to be writing u of t because it's easier to talk about time. But as a general statement, the first thing we're going to be looking at, and it's going to take the majority of this course, is we're going to look at functions of one variable. And then we'll look at how the derivatives of this function match together in order to define a differential equation. When we're talking about derivatives matching together of a function of just one variable, we talk about ordinary differential equations. They're ordinary because the only type of derivatives is the derivatives with respect to x. If a function has just one variable, there is just one type of derivatives we can take. On the other hand, we can look at functions of more than one variable. So we can have a function u that depends on x, y, z, maybe it depends on t or some other variables. The key element is that it depends on more than one variable. Then we have a differential equation that takes into consideration the variables, x, y, z, and so on, the function itself, u, and all possible partial derivatives. So we have the derivative with respect to x, the derivative with respect to y, with respect to z, the derivative with respect to x twice, the second derivative with respect to x, or the derivative with respect to x of the derivative with respect to y of u. All these are partial derivatives. When we have partial derivatives, we talk about partial differential equation. Let's dial back a little bit and look at possible notations. Notations, when you're talking about derivatives, can be a bit overwhelming because there are a lot of different ways of indicating the same thing. So if u is a function of just one variable, we can indicate the derivative of u as u prime, u dot. U dot is often used when the variable you're relating to is the time, or derivative with respect to x of u, or just derivative, partial derivative of u, without any information about the variable, because the variable, there is only one. Second derivatives can be either indicated by u prime prime, or u dot dot, of derivative with respect to x of u, or derivative with respect to x squared of u. We can also have the nth derivative, and we notated it by u at the power of parenthesis n, or partial at the power n applied to u. These are all different ways of indicating derivatives in one dimension, so with respect to just one variable. Or we can have functions of more than one variable. So in this case, I'm talking about the variable t, x, y, and maybe others. When we're talking about functions that are functions of time, and of other variables, time has always a special place. So we talk about the derivative with respect to time as u dot. When we're talking about just one variable, then we mix things a bit. But when we have more than one variables, time is on its own. So we can have the partial derivative with respect to time of u, and we usually denote it with u dot. And then we have the partial derivatives. So partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to x and y. And then we have second derivatives. If we have the partial derivative with respect to x and x, we might notate it as dx squared. So this is all the notation we're going to be using. Let's go into linear differential equations. We say that the function of multiple variables is linear in x if rescaling x by a factor a rescales the value of that function. So f of a multiplied by x is equal to a multiplied by f of x for any value of a. A is a real value, and that allows us to rescale everything. If that happens, we call it linear. So you can imagine that when we talk about linear differential equations, it means that our differential equation that we denote by capital F is linear, and it's linear with respect to u and all its derivatives. We don't care about it being linear with respect to x, only with respect to u and its derivatives. If that happens, we talk about linear differential equation. Another type of equations that we're going to be seeing is systems of differential equations. So we're talking about a situation in which we don't only solve for one function, we solve for multiple functions at the same time. So for example, here we have the function u and the function w. Then we have one differential equation on u, w, derivatives of u and derivatives of w equal to 0. And then another differential equation also on u and w equal to 0. If we have more than one equation with respect to more than one function, then we talk about systems of differential equations. The order of a differential equation is the order of the highest derivative in that differential equation. So let's make an example. If we're talking about an ODE, an ordinary differential equations, so we are taking a function u of x, and the differential equation is u plus 3 times u squared plus third derivative of u equal to 0. This has order 3 because the highest derivative is the third derivative. In order to make things more comfortable to look at, we often rewrite the ODE that we gave in an implicit form, so is a function of x, u, and all the derivatives of u equal to 0. We turn it around to take away the highest order and put it on the side. So we have u, the nth derivative of u, equal to a function of x, u, u prime, u second, up to the nth minus 1th derivative of u. This makes things easier to look at. We immediately see the order of the ODE, and it makes things easier to work with. What is a solution to an ODE? The solution of an ODE is a function that you can fit inside the ODE and it makes sense. But what is different from a normal algebraic equation? The difference is that when you're talking about the solution of an ODE, you talk about the solution within a certain bound. So you're looking at a function phi of x, where x is between a and b. And you're solving the ODE for x between a and b. So when we're going to be talking about solutions, we want to be clear about the fact about where we're solving the ODE.